I'm recording.
Okay. Hi, I'm Lenora.
I'm Zoe.
And I'm Julian. Today we're going to be presenting our text, Ambitious Science Teaching. This offers a cyclical framework for creating engaging, rigorous, accessible curriculum for students in any science classroom. Some of the methods in this text are subject specific. However, many of the skills and practices are applicable for any educator striving for student-centered, discourse-driven, collaboratively designed units that challenge educators and students alike to be ambitious thinkers. Before we get into our presentation, I want to offer a bit of a roadmap. Ambitious science teaching is structured on 4 core principles: planning for engagement with big science ideas, eliciting student ideas, supporting ongoing changes in student thinking, and drawing together evidence-based explanations. We will expand on each of these in our presentation. Additionally, we will highlight 4 skills: discourse moves, modeling, scientific argument, and collaborating with colleagues that are critical for implementing ambitious science teaching curriculum. These principles offer a cyclical framework, creating ongoing opportunities for teachers to refine their practice. And with that, I'll bring it to Lenora.
All right, so core practice 1 is planning for engagement with big science ideas. And the book talks about using something called anchoring events as a way to structure units, where each activity relates back to this one big event. These events are real-world phenomenon instead of just topics. Anchoring events can be historical events, current events, everyday occurrences, and they can even relate to social issues. They are context-rich and specific, and they are compelling and relevant to student lives. Instead of using a topic to build a unit on, such as the ideal gas laws, an example of an anchoring event used in a physics class is shown here with the picture of an imploded steel tanker. Students are shown a video of this occurring, and it's presented kind of like a mystery. Why did this happen? They spend the whole unit making observations, doing activities, and more to eventually be able to understand and explain exactly why this happened. They will, of course, learn about ideal gas laws along the way, but in a more grounded and fun way. This relates to Freire's problem-posing model of education, which rejects the banking model. Anchoring events depict a non-static version of reality and show that science is happening every day in all of our lives. Thinking about science phenomena this way also requires higher level thinking and critical thinking, which is another way that ambitious science teaching rejects the banking model of education. On to the second core practice, eliciting student ideas. In order to encourage participation and really have a dialogic learning community, we need to create an environment of safety and civility so all students feel comfortable sharing their voices. The book mentions a few ways to do this. One that really resonated with me was co-creating classroom norms with students, specifically in the categories of respect for others, equitable participation, and accountability to science as well as to one's classmates. It can also be helpful to explicitly ask students what might prevent them from participating in a discussion, possibly by using an exit ticket. That way you can address specific needs and barriers. Another way to encourage participation is by activating prior student knowledge through the way activities are structured. Students come into class with a whole life of background knowledge and experiences and interests, and we want to draw on that instead of just replacing them with what the teacher thinks is important. Students can really learn from each other this way. Another way to elicit student ideas is by starting with just asking for observations rather than asking students to come up with complex explanations for these science phenomenon. Back to the steel tanker example, most students would be able to observe what is happening either visually or auditorily, while maybe only a few students might be able to explain exactly what's going on. By starting with observations, all students can participate and we can collectively build up to hypotheses and explanations. And while students are sharing their voices, either observations, explanations, we want to avoid evaluating the responses by signaling for correctness or incorrectness, because this discourages further participation. Finally, another technique to use to encourage listening and intentional talking is the think, pair, share routine, where students think quietly to themselves and then share with a peer, and then some share to the class. This idea is echoed in Bell Hooks's work, where she explains that using this method can ensure that all student voices are heard by at least one other person every day of class. And finally, the book talks about talk and having the teacher use discourse moves to support students through this complex process of learning to talk science. Some of the specific examples here are follow-ups, asking students for more information, pressing, asking students to go a little deeper, and crosstalk, which actually opens up students talking to each other in the classroom, which again decenters the teacher as the sole authority and knowledge giver. And now we're gonna go over to Zoe to talk about modeling.
So modeling is a skill in ambitious science teaching that is very important. This skill really connects core practice 2 of eliciting student ideas to core practice 3, which I'll talk about in a second, but is supporting students' changes in thinking. In this context, modeling is a visual and written explanation of the anchoring question or anchoring event. So you can see this diagram on this slide is showing a student's kind of first try at modeling what they think is happening in the steel tanker example that Lenora gave. Another important part of modeling in this framework is sharing and revising. So if we can go to the next slide. This slide is 2 diagrams. The first is a student's first try at modeling an anchoring event. So you can see they do a drawing, they have some written explanation, they have some arrows kind of showing like upward force. And then this second one is near the end of a unit, and they have a more complete and longer written explanation. They have a zoom in that shows all of the forces happening, and it's just much more detailed. And so this sharing models, revising models throughout the unit is the way that is a way to show how students are changing their thinking in response to what is being taught. So that kind of brings us to the third core practice, which is supporting ongoing changes in students' thinking. So this is really based on the idea that if someone has an incorrect idea, you can't just really stamp it out with a correct idea and like stamp in the correct idea, kind of the banking model. It doesn't really work like that. That's not really how people learn. So this idea is that changing students' thinking requires that they actively engage in the sense making of what they're learning. And so it's really about like learning how to learn. So supporting ongoing changes in students' thinking relies on 3 practices that are kind of shown in this diagram. The first is introducing new science ideas. So the text acknowledges that there are certain things that are happening that are not directly observable by students. And so it does say that there are some things that might have to be given to the student through direct instruction, but it makes this distinction and actually calls it interactive direct instruction, and gives a lot of tips and tricks on making direct instruction engaging and fun for students. The second part of this supporting ongoing changes in students' thinking is engaging students in activity and sense making. So activities in the context of AST are labs, investigation, hands-on work, and a whole host of other types of activities. The main thing that activities are not is cookie cutter investigations of arbitrary questions. Really the point of activities in this model are that they will support some part of the explanation for the unit's anchoring event. So for each basically each activity that happens directly relates to the anchoring event in that it helps a student understand one part of the final explanation for that event. The cool thing about AST is that it also acknowledges that you can't just do activities and expect students to get what you want them to get out of them. So equally important to activities are that sense-making talk that happens after, before, and during the activity. So this really relates, as Lenora mentioned earlier, to like the dialogic method of Freire. And so that first sense-making talk happens in small groups where students are doing the activity and the teacher is going around among tables and asking certain questions to press and follow up on student ideas and deepen their understanding. And then that sense-making talk kind of moves from small groups into bigger groups, which is this third practice that is mentioned in this diagram, which is collective thinking. So that looks like whole class level debriefs on activities where the whole class is going through, okay, what did you see happen in this activity? What patterns and observations did you observe? What caused those patterns or observations? And then really important, how does this help us think about our essential question or anchoring event? And that brings us to scientific argument with Julian.
Thank you, Zoe. In addition to the key skills that Zoe mentioned for supporting ongoing changes in student thinking, another critical skill is scientific argumentation. Students don't come to class with an understanding of the structure of scientific argumentation that is used in real-world scientific communities. Therefore, it is critical for educators to explain, model, and encourage scientific argument. The goal is for students to engage in peer-to-peer scientific argumentation, expanding their social learning and empowering students to press for scientific explanations for themselves. This further supports the Freire and Bell Hooks model of social learning in the classroom. This begins with the scientific argumentation begins with an invitation to argument. When a student wants to contribute, they should follow this sequence. First, there should be an explanatory claim. This is just an observation of the event that can help explain some sort of pattern that they see within it. After that, they have to submit some sort of evidence. This can either be firsthand evidence, like just observe, a detailed observation from the explanatory claim, or it could be secondhand data that can come from a scientific paper that was shared in the unit. After they submit that evidence, they have to connect the evidence to the explanatory claim using supporting reasoning. And this connects the data to the observations by using known concepts, facts, and principles that have been either submitted in the unit or that the students have from their own scientific experience. And with that transitions us into core practice 4, which is drawing together evidence-based explanations. After students have developed the scientific knowledge, hypotheses, and models required to address the big idea in the unit that was presented in core practice 1, we must draw together the knowledge with the goal of students creating a gapless explanation for the anchoring event and for the big scientific idea. The critical tool to accomplish this goal is a gotta have checklist. The students often have difficulty drawing on all of their scientific knowledge alone. The gotta have checklist allows students to collaborate on the key information that they have covered in the unit together with the rest of their class. The teacher asks, what are the things that we gotta have in our explanation? And the class freely contributes, edits, expands on the list. Furthermore, the gotta have checklist then becomes the primary resource to create the final revisions for the models and explanations that they have continually been revising throughout the unit. Next slide. In addition to the checklist, a teacher has to ask what other resources are going to be available for the students. Are they going to be revising in pairs, or are they going to be revising individually? In general, educators should tend to have more resources for the students to draw upon because it empowers the students to look for scientific answers or explanations themselves, and because it more accurately replicates real world conditions for scientists attempting to explain real world phenomenon. After they have developed and assessed their explanations, we have to assess for understanding of those explanations, which brings us to our next slide. There are 5 key principles for assessing understanding. I won't be going over all 5, but I will be highlighting 2 of the most important. The third principle is making sure that the criteria for success for the explanation or model is clear and explicit. If you don't explicitly state that a concept or a process or a fact is required for the final explanation or model, then you should not be assessing for it. It is important for every single student to understand what is expected of them to have in the final explanation or model. Otherwise, it is you should not be assessing that understanding. And finally, the 5th principle is ensuring equitable opportunity to show knowledge for all of the students. You should not be relying only on text-heavy questions that are intentionally confusing, nor should you be requiring paragraphs of text-heavy explanation. Instead, you should be giving multiple avenues for displaying knowledge, including pictures, diagrams, cartoons, and written words. Furthermore, each mode of representation should still follow principle 3, i.e. making sure that every single step along the way is clearly and explicitly shown what is required for the students to know, whether they are drawing a cartoon or a model or writing it out in words. Principle 5 is critical for universal design in learning, which brings us to our final skill, which is collaboration with colleagues. This skill acts as the bridge for the cyclical framework of ambitious science teaching, and it allows for continual ongoing refinement via data-driven colleague-to-colleague collaboration and intentional goal setting. This skill is organized along the plan, do, act cycle. First of all, in the plan phase, you develop a monthly plan for enacting a sub-practice. And a sub-practice is just a specific change targeting a specific learning outcome goal that is measurable via data collection. And the way you collect data should be using some sort of exit ticket, tending to be more of a formative assessment. When you give students an exit ticket, it's important to note to them, the reason you're giving an exit ticket is because you are a learner in the process just as much as the students are, which further empowers the students to understand that educators are not the end-all be-all suppository of knowledge. They are always continually trying to improve their learning and teaching. After the exit ticket is provided, and you have decided a sub-practice, then you transition into the do phase, where each member of the cohort enacts their lesson plan and then gathers the data using the exit ticket. After that occurs, the colleagues gather together again and examine data, look for patterns or trends from the exit tickets to assess what new practices should be included to try to further improve. That is the act stage of the plan, do, act cycle. Essentially, in the act stage, all the colleagues are trying to assess is what might we try to do better to better support our students. Again, this brings us all the way back to core practice number 1 and shows that the ambitious science teaching framework is cyclical and allows for continual improvement with colleagues.
And so wrapping up, we wanted to give some connections back to this class as well as other classes and give our final thoughts. So overall, we think AST offers rigor and equity and really rejects the banking model that Freire and Bell Hooks talk about. We think that it leverages student experience and knowledge, which connects to a social constructivism model that we've been learning about in 612. AST is really compatible with universal design for learning, which we've been learning about in SPED 511, because it offers multiple ways to represent and act on knowledge for each of the 4 principles. We really do recommend this book, especially to other science educators. If you are a science educator and want to enact ambitious science teaching, you probably do have to read the whole book. And finally, we do want to acknowledge some critiques about this book that we had that kind of made it a 4 out of 5 stars for us, which it does advance kind of a more Western and American view of science. It subverts this a little bit because it does talk in depth about like treating students' knowledge and previous experience as a big resource, especially in core practice 2. But we do think it could go further to deconstruct the colonial framework for science. One thing that it misses is kind of incorporating calls to action for students. So it ends up falling more under just student-centered curriculum and doesn't inherently reach to the level of curriculum for social transformation. But there definitely are opportunities for ambitious science teachers to incorporate that aspect in and make this curriculum even better. Thank you.
Thank you.